I'm John Muth, and like Bina, I'm from NC State University. I'm a professor in electrical engineering, and I'm a deputy director of the SIS Center. And today I'm going to give kind of a high-level overview of some of the energy considerations of self-powered devices. And so I'll try to define what a self-powered system is. I'm going to talk about wristwatch, because that's something I think everybody knows something about. We're comfortable with using them and those types of things. And then I want to kind of examine the system-level energy in kind of a human context. And so we'll talk a little bit about energy generation. I'll spend a lot of time talking about thermoelectric as an example. I'm not going to spend a lot of time talking about energy storage, but talk about a few points. And then some of the things that happen as we consume and use energy in these types of devices. And power management strategies. I think I'm kind of run out of time to get into a lot of detail about that, but that's obviously a very important part of these types of things. The SIS Center is a lot of different organizations, and I'll highlight some work from different members of the center. But really what we're trying to do is we're trying to put together a self-powered system. And so if you think about it in our schematic of what of our test platforms, we have energy harvesters, which might be thermoelectric or piezoelectric. We've got low-power electronics, which is a system on a chip, kind of integrated low-power type system. It's going to have to communicate. It has an antenna to be able to talk to other things. And then we need to have low-power sensors. And then, you know, the hard part, in a sense, is if you can do all these individual pieces right, how are you going to put it all together in something that's wearable and usable? So when we were writing this proposal, one of the things that we were thinking about is some of the big trends that were happening. So if you think about it, energy harvesting has been kind of increasing pretty slowly but consistently over the years. Energy storage, batteries are kind of static for about 100 years or so. And then now recently we're starting to see big improvements in batteries. But we also have the advent of supercapacitors and new hybrid battery capacitor type devices. And then something that's changed all our lives is looking at power consumption in terms of computation, but then the other things that happen in terms of how we handle information and send it around. So let's see. I think I'll go back to that. Well, I'll go. Pardon. If you think about the sensor system, when you look at this, you know, basically we have transduction, computation, and communication, and we've kind of evolved from having analog systems that transduce a signal to something that displays it. So you used to go from a pressure gauge that would move a needle. You now have systems where you've got something where you have some signal conditioning, and then maybe an analog voltage that then can go to a display. Or maybe analog to digital, and then some signal processing to improve your sensor. Then maybe that goes out via radio or cable to something, and then to a display. Or you have analog to digital signal processing, and maybe you do a lot of processing on the chip, or you do a lot of things that have to do with the context of how the sensor is being operated, compensate for linearity and that type of thing, and then send it maybe to a radio to a display. And so if we look at all these types of things, we have kind of different energy schemes and different energy relations that end up being important. For instance, can we do the computation on chip before we have to use the power in the radio? So when we were thinking about these types of things, we decided to apply a very simple constraint, and that's wearing it on the human body, with the constraint of how much energy can you extract comfortably from the human body. And this implies two things. It implies that it's got to be close to the body, so you've got all these human interface type issues, and then you've got social acceptance type things. But if we plot here power versus year, what we find is that the digital signal processing and computation part is essentially becoming free. And so if we add that to our analog to digital conversion, that essentially kind of goes away. If we take a look at our radios, what we see is that the same thing is starting to happen, that if we can continue to improve our analog to digital conversion, start to push those types of electronic systems down, we'll be limited by radios. And that gives us kind of this composite curve. Now, what we realized is if you look at some of the energy harvesting, if you look at current thermoelectric technology today, you can get about 40 or so microwatts out, and that creates a system space in which you can operate. So, one of the goals of our center is we want to be able to push up the amount of energy that we can get from the body, and we want to push down as much as possible the amount of energy that we're using. Okay? And this is changing rapidly, and as Vina mentioned, if you look at today's scenarios, the radio consumption is dominating the power. But then as you add multiple sensors, and as you start reducing the amount of power that your overall system does, that's probably going to change. You're going to start having some more analog front-end type things start to take a larger portion of the what's going on. The interesting thing, though, is that you can also do computation. Can you also push down the amount of information that you actually have to transmit? If you start adding sensors into the mix, it starts to get even more complicated. And this is just kind of an example showing that your analog front-end stuff goes up. If you have a limited, similar amount of powers for sensors, but have multiple sensors, you start to consume percentage-wise larger amount of that. So again, there's also other issues with radios in terms of if you're using Bluetooth 4.0, what does that mean when you go to your next generation radios? How are you going to be compatible with everything else? So looking at just in general, we need to have a balance. If we can harvest enough energy from the environment, then maybe we could operate things for very long periods of time. To do that, we need to have the ability to store energy because our harvested energy isn't going to be reliable. This energy management issue becomes important. It's going to be more than just duty cycling to reduce power. You're going to have to do other things that also manipulate the information in ways that save power. And then when we get to this whole thing, there's also really interesting questions as to what the performance of your sensor system needs to be for a particular application and how that affects power. And so hopefully we'll discuss some of these things. So if you take a look at the battery and lifetime issue, this is from 2003, University of Utah. You can see that even if you have rechargeable batteries, on the year kind of time scales, you start to run off. And so one of the interesting things about capacitors is that you don't necessarily have, you have different types of degradation as you have your supercapacitors go through their charging and recharging cycles. And so that creates another opportunity to be able to get rid of some of these effects of having that you have with batteries. Supercapacitors also have issues, but this just points out that under reasonable voltages for modern electronics, that you can have lifetimes that extend into the years under different things. So, getting to the point, what is a self-powered system? I think that requires a little bit of a definition. It's not necessarily obvious, but what I kind of came up with is after initial startup, it's a system that can continue to function, or some subset of functions, for an extended period of time by obtaining energy from the environment, and if the conditions are favorable, it can obtain more energy than it started with. And then you might have two different types of self-powered systems. You might have systems that require no human intervention, and you have other systems where you require some type of intervention that be required. That might be replacing a battery. It might be winding up something. It might be shaking something, moving something. And so if we start thinking about those types of things, we can consider something like a wristwatch. It's a sensor system. We want to know what the time is. The task is relatively simple. We want to move hands in constant rates in a very simple way. Or maybe we want to change a display at periodic intervals. And so we kind of have two different things that we can compare, a pocket watch or a very thin e-ink watch. If we take a look at the analog watch, the mass of a hand is much less than a gram actually, but you can have, figure out what your potential energy is, divided by the time, add in some overhead. You find out that, a watch is only consuming typically microwatts of energy, and so it's a nice example of a low power system. Similarly, what you can do is you can take a look at your e-ink watch type thing, and you can do the same type of calculation. And if you do that, you again find that you end up on the order of down in the microwatts of energy. Okay, so when you start thinking about these self-power systems, it's sometimes interesting to go back to your first year physics fundamentals and start to think through where's the power being expended and how are things being used. Obviously we could do this for a lot of different things. And then in the case of watches, there's also a long history of having, wind-up watches or self-winding watches or thermoelectric watches, solar watches, and then, of course, batteries. So what they have in common is that they'll have different characteristics of how the energy is expended over time. So if we think about our mechanical system, we have some amount of energy that's wound up, and then we have some type of energy loss. We have some operating time, and then maybe some time where we have a margin where we could rewind it, and then at some point the system stops. The details of this energy dissipation, vary from system to system. So we can go ahead and, the shape of this type of curve, and so maybe this is a little bit of an exaggerated loss here. Maybe it'd be more linear like this, but just to kind of give you an idea. But it illustrates, for a battery system, you have a certain amount of commonality. For a coin cell battery, if you've got a relatively large one, your watch lasts a couple of years. So essentially there's no human intervention being able to, get to this, and it only bothers you a little bit that you have to go ahead and change that watch battery. And so that's what you do. You have some amount of operating time, you switch your battery, then you do it again. Now, if you're recharging rather than replacing, it starts to get a little bit more complicated. You could say, well, I'm just going to recharge it in the same fashion, but you've got questions: are you fully recharged or you're not? Is your ability to recharge over time going to decrease? And so that's going to impact how things operate. So maybe more realistically, what you have is some type of time where you're operational, some time where you've got to take your phone out and you've got to plug it into the wall and you're not using it because it's tethered to some type of system. So there's this big question of where do you get your functionality if you have to take action to be able to recharge your system. Okay? And there's a whole other issue is what if you initially start out your system with no energy, and then you're going to have some type of energy source, and you want that system to start up. How's that going to behave? And even simple things. Do you wait until it's charged up all the way, or do you wait until it's only charged up a little, but then you have no reserve, and then you'd have to repeat this cycle? How do you build up your energy? All becomes different types of issues. Similarly, if you forget to bring your charger with you on a business trip or whatever, or you leave your watch in a drawer or something like that, again, you have these issues about, what's your history of behavior and the context of which someone's using the sensor system to be able to understand how to power the system. So for a watch, it's pretty simple. Is the watch on? Is it going to work when you take it out of the drawer several months after sitting around? Is the time accurate? The metrics are pretty easy. And then you've got all these secondary metrics. Is it comfortable? Does it look good? Is it expensive? Is it something I like to show off? Is it exclusive? And so these guys have actually spent a lot of energy, so to speak, looking at these types of things. So you have automatic movements where you have kind of an eccentric gear that oscillates. You've got photovoltaics that can go ahead and you have your watch sitting under in sunlight or in the sun. And as long as you don't have your watch with your sleeve over your watch, you're building up power reserve. You've got thermoelectric watches. This is from the mid-90s. I'll show a little bit more about it in a minute, but basically you have these thermoelectric modules that are in contact with the skin. You've got a thermal insulator between the skin and the watch here, so you have a hot side and a cold side. Okay. And then just to talk a little bit more about the different types, looking at this Seiko watch, for instance, with this eccentric gear, you've got this kinetic movement that is going to oscillate, translate linear motion into a rotational motion. And what they've done here is they actually have a hybrid system where they're taking that mechanical motion, they're winding up a spring, that spring gets to a certain point, then it goes ahead and it spins a little dynamo. And so then the dynamo creates electricity. And so what happens is that you get several minutes or several milliseconds of a pretty high voltage and a pretty high current density. And then you can store that electrical energy into a capacitor. And then you can generate energy. And so earlier there was a question about pacemakers. Pacemakers use about 8 microwatts to be able to coordinate the electrical impulses across the heart. And so there's a group in Switzerland where they have nice watch companies. What they did was that they took a switch mechanism, actually attached it to a sheep's heart after modification, and were able to pace the sheep's heart in vitro or in vivo. With the thermoelectrics, this idea has been around. This Bulova example actually illustrates some of the critical problems that I think self-powered systems face in terms of not understanding the system. They actually caused major financial difficulties. They invested a lot of money in this, but they didn't have a mechanism to, once the battery went dead, to be able, you had to send it back to the factory to get the battery replaced. And then they ran into some other types of issues. But, this is early 80s. You've got thermocouples here that can have the hot side and cold side to produce the power, and the Seco watch that we mentioned earlier. Okay? And then the photovoltaic, you've got an amorphous silicon solar cell here. Again, it has a battery in the system for energy storage. They could have used the capacitor. In this case, one of the things that they worked on, they made the solar cell less and less visible over time, and it's gotten buried deeper and deeper in the watch to be less intrusive. So the light actually has to make it through the watch face, and it's got to go through kind of a translucent material before it actually hits the thing. And the power reserve of the battery is on the order of about 6 months. And then it's got a variety. It's smart. It has. It can go to sleep. If it starts to detect that it's low in power, rather than sweeping the second hand in a continuous motion, it moves it in 10-second intervals. Okay. If you want to, a lot of these watches are very clever. If you want to find out how much power you have, you press a button and it moves a hand to show you where how much power you have left and what your reserve is. So there's lots of good things to learn from these types of kind of simple sensor systems. And it's a good example to illustrate, the human context, because we use watches indoors, outdoors, whether active or infirm. All these things, I think, are things that we're seeing. So what we can also find out is that these things create problems. If you leave your watch alone, how are you going to charge it? It has no battery or if you have no source. So there's actually a market for self-winders for watches. If you go to a watch store, they've got racks of these things because they have to keep all the watches wound up, right? And some of them can be quite complicated and desk-like ornaments, but or you can make your own on the internet. So it's kind of I like the Lego version, but that's part of the context. The next context is the human dimension of energy. So once I started working on this stuff, I bought a Fitbit, and I started running around. And so this was a fairly active day recently. 23,000 some odd steps, about 11 miles as I went around. I started off sleeping, I went for a run to Starbucks, I had a coffee, then I ran back home, got in my car, had a meeting, I think, with Vina, got back in my car, went to the state fair. Actually surprised about how much activity is just walking around the fairgrounds. Went to my office, had a nap. Leander woke me up. Had to walk around the building to find different stuff we'd misplaced. Went home, had dinner, so on and so forth. And then I had a late night walk. Okay, so we can translate that basically to some rough estimate of the amount of calories that are burned to connect to those types of activities, right? So you can say that I've got some baseline metabolic rate, and then my activity is related to that through some formulas. And that's what all these companies are doing. These activity monitors are really working hard on, is trying to figure that out. Because they're all basically wrong. I mean, if you talk to real exercise physiologists, you'll hear real wide variety of different numbers as to how they are, depending on where you wear it on, your hip or on your chest or it's very different. It's actually very complicated, but it's very useful. So the precise number isn't maybe important, but I can tell, very clearly if I've got a day like this where, I was basically lazy and I had a very low energy day, okay? And then, you've got this, so in terms of monitoring health, it's you don't have to necessarily have very high quality information to be able to track whether you're burning more calories than you're eating. But if you start looking at things like, how does that energy availability impact? For this high energy day, if I'm looking at the thermoelectrics, when I'm asleep, I don't really, I'm not producing a lot of energy. If it's dark or if I'm indoors and the lights are off and I'm under the covers, really I'm not producing much energy. On the other hand, if I'm, running, I'm producing a lot of kinetic energy that potentially I can go ahead and capture. If I take a look at, these intermediate activities, maybe I can get something, maybe I can't. It also depends on my environment. If I'm indoors or if I'm outdoors, the issue of photovoltaics, if I'm outdoors and I've got a nice sunny day, I can produce huge amounts of power compared to the scales of what we want to use. If I'm indoors in a room like this where we're pulled the drapes, it's a much more difficult proposition to get large amounts of energy from light. And so the difference between that high energy day and this low energy day, if you take a look at it, is actually about 60 or 70 watts on average over the 24 hours, or it's almost 6 million joules. And so the question is, how much of that can I capture? And if I can capture, even a percent of that, I'd actually be in pretty good shape on the high energy day. On the low energy day, again, it's a little bit more difficult proposition. Okay, so this brings us to what energy is available on the body. We've got heat, we've got motion, the ambient light I mentioned. Directed energy, I think it's a little bit in a different category. If you want to have an implantable device and you want to go ahead and use ultrasound or infrared energy to supply energy to that device, you can actually get large amounts of energy delivered very efficiently, relatively speaking, to the device. And so people interested in issues on pervasive computing have kind of looked at this stuff for many years. But you can see footfalls, this moving, 170 pounds walking around at a reasonable pace produces large amount of energy. So I'm going to go into depth on the thermoelectric example because it's a little bit more complicated, but I think it illustrates some of the other issues with other energy harvesting mechanisms. The thermoelectric effect is when you have two dissimilar materials where you can generate a Seebeck efficient when they're at two different temperatures. Traditionally what we've had these very hard ceramic substrates that we have these p-n junctions, so the two different semiconductor type materials form a couple, and then the hot side and the cold side will have a voltage, and of course we have heat flow going through that. From a science point of view, one way to look at how these can be compared to each other is to have a figure of merit, which is the electrical conductivity times the Seebeck coefficient squared. Seebeck coefficient is basically the coefficient that's proportional to the temperature difference, or you can see the voltage proportional to the temperature difference, divided by the thermal conductivity. And so if you look at this Z metric, what you have is you find out for insulating materials, you tend to have high Seebeck coefficients, whereas for metallic materials, you tend to have low Seebeck coefficients. And for metals, you tend to have high electrical conductivity for metals and low electrical conductivity for low carrier concentration. So it turns out that heavily doped semiconductors are the sweet spot to be able to have high ZTs. when you start thinking about the thermal conductivity, this was kind of the big breakthrough in the early 2000s, is that people figured out that if you have means of disrupting how the phonons travel through the material, so this is where your nanoscience comes in, you start to lower that thermal conductivity, which means you can sustain the temperature difference across the material, so then you can have that voltage. And that's reflected in this being in the denominator there. If we take a look at different materials, you find out that they all have different optimal ranges of operation. And so if we're talking about human-powered thermoelectrics, normally we'll be talking about bismuth telluride. There's some reasons where you might be able to use some of the lead tellurides and other lead-based type compounds as well, but typically you're going to want to have a material that's suitable to be on the body. So that's some of the science. If we start looking at the engineering, again you see you've got your Seebeck coefficients give you basically a voltage. The voltage in series will scale to the number of couples. The resistance also goes in a series type fashion. And the thermal conductance, though, is inverse to the resistance. So if we take a look at the size of this couple and the length of this couple, what we find is that if we increase the area and decrease the length, we'd improve lower the resistivity, or lower the resistance. And that might be useful on the electrical part. On the other hand, when we do that, when we increase the area and we lower this length of the thermocouple, the thermal conductance is no longer where we'd like for it to be. So there's an optimum here that you have to trade off in terms of being able to do that. What it happens to turn out to be is that the optimal number of couples depends on the square root of the ratio of the load resistance to the lead resistance. You also have to consider the Carnot efficiency, and the ZT gives you an overall efficiency there. You've got to have impedance matching of the system. So if you, for a given resistance and a given voltage, you'll have an impedance that you'll want to match to be able to have efficient transfer of power. And so similar to solar cells, you need to have a maximum power point tracking. And then finally, a lot of times these Seebeck coefficients are in the microvolts. And so even if you have a large number of couples, you may be at millivolts. And then if you're at low temperatures, you have an issue, right? So if you're going to boost the output of the thermocouple to a usable voltage, you'll need to take that into consideration. And then your efficiency may drop for your thermocouple. So you can buy boost converters, certainly. This is a kind of a nice one from TXL Group, but you've got about an 80 millivolt input for that. Linear Technologies is an integrated solution. They're playing a little trick here by putting a transformer in here because the Thermoelectric is a DC source, and for them to be able to get the efficiencies up and be able to boost that voltage, by having a little micro transformer that's outside the chip, ends up letting them do that. And then you have some other things to consider about in your system. How's your voltage going to change as a dependence of your charging time? What's the efficiency going to be? In a lot of other systems, efficiency really drops off at lower voltages. But this linear technology chips, for instance, they actually have a higher efficiency, about 50%, which is low for a boost converter compared to other systems where you might use boost converters. But when you get up to these higher voltage range, you're back down to 10%. So when you put these types of systems together, you have to look at these types of details to be able to maximize the power. Other types of thermal boost converters, it'll go the other way. You'll have lower efficiency at lower voltage. So you change the temperature, you're exercising, and then you're sitting still. The output voltages are changing. So again, you need to have some type of tracking mechanism. So all this kind of boils down to, how much thermal energy is practical to get. You put out about as much light as as much thermal energy as a light bulb. So a big person might put out about 120 watts. We can go ahead and take a look at the Carnot limit, right? Basically, we have a heat engine here. We have some difference in temperature, so we can go ahead and look at the thermodynamic efficiencies. You know, a person about my size has about 1.75 meters squared area. So that knocks us down. If we look at it, we're down to sub-milliwatts, especially if we're in these lower areas. So what I could say is, well, you know, I'm not going to cover my whole body in some type of, you know, skin suit or balloon or something. It'd be ridiculous. But you know, some areas on my body radiate more heat, and so if I do that, I actually can boost that up a little bit. And so in my wrist, I have all the blood flow to my hand going through a radial artery. So there's actually a hot spot that could be exploited. And there's other places in the body where you can exploit that heat. So then we get to the issue of where could you use these types of systems. If we want to push, gallons and gallons or liters of blood through the body, through all these little tiny capillaries, you're talking large amounts of energy. You're just not going to be able to do that. Having something like a defibrillator where you've got maybe a high voltage, high currents issue, unlikely. Then you've got other things like retinal implants, conventional pulse oximetry, neuronal recording. Then it becomes a little bit more questionable. It's just we have an issue with our present technology today. Could we make these lower power technologies and then be able to get below this limit, or do we have something where there's a fundamental physics that says that we can't get there? If we look at hearing aids, this is something where the industry's been driven extremely hard by having low-power systems, and so there's been huge amounts of progress. And then, you know, if you're coordinating electrical signal like a pacemaker, we're probably there today. So in the center context, what we're trying to do is try to push some of those technologies down into these power ranges that we can go ahead and start to use these types of energies. And it's probably not completely far-fetched for the right system design where you take things into consideration carefully, because if you look at the outputs on the spec sheets of Thermoelectric, the amounts of power that you can get if you scale them up to about a square centimeter area starts to approach that. Okay, so what are the problems? That's what the data sheet says. What do you actually have to do? Well, if your core body heat is a heat source, what you have is a variable skin resistance. Then you've got the thermoelectric, where you need to maximize your delta T. Then you have an issue of what your cold sink is. You know, what's the resistance of being able to get that heat transferred out to the environment, to that cold sink. And so basically, you can think of this as having a source and then two variable resistors, and you're trying to maximize the temperature across your thermoelectric. Sweat, your body is very efficient at keeping heat within the body if it's cold. You actually can change the thermal resistance of the skin by over an order of magnitude easily. You start running and you have convection. Again, you can start having or a little bit of evaporation to help you out. It's a very dynamic situation. You work through all this, it really looks like getting 40 microwatts today in a wristband is practical. If you're running and expending energy, boosting your heat source, and you're improving some of these thermal considerations, getting 300 microwatts is not unreasonable. So to do just a quick example, around your forearm you have maybe about 10 milliwatts per centimeter squared. These are kind of some numbers pulled out of the literature for kind of somewhat typical values for the resistance. And we can say, well, what if we have a temperature difference of about 10 degrees C? So I can sum up, I can say, well, the sum of all my temperature differences should be 10 degrees. If I didn't have a thermoelectric in the system, if I take these resistances and I've got a 10 degree temperature difference, with no thermoelectric I'd have about 6.5 milliwatts per centimeter squared going through that system. Okay. If I put this relatively low resistance thermoelectric into the system, it changes. The amount of heat flux going through the system, I now have more resistance in the whole system, so the amount of heat flux going through the system drops. So, you know, the resistances that I have is, and the temperature difference is dictating the heat flow that's going through the system. So the interesting thing here is that your delta T that's usable on your thermoelectric is less than a degree. So it's not a whole lot. If I go ahead and I start sweating and I start you know, running to improve, and I do something to improve the convection as well, and still say, well, you know, my environmental temperature is still a delta T of about 10 degrees, and I go through this together and lower these numbers, what I find out is that now my heat flux that would be going through my system, determined by the temperature and these resistances, is now 12 milliwatts or so. But that's more than what I said I had, right? And so if I only had 10 milliwatt available, per centimeter squared available, basically what that's supplying me is, although the heat is, you know, I've improved my temperature difference across my thermoelectric, so I'm going to produce more power. But I can also be in a situation where I could actually end up starting to pull heat from the body. All right, so that it becomes another issue. So you have to start thinking about this. And at IMEC several years ago, did some nice work, and I think I have a picture later in the presentation where we've got some examples of what happens. And so here, this is air temperature on this axis. So your body's maybe somewhere around 35, something like this. And then this is after going through, this is probably more interesting to look at, the same information but in power. You know, you're producing in a kind of a sedentary type environment about 10 or so microwatts. And you can get maybe a little bit better than that. If you start going outside and you start moving and you start walking around, all of a sudden you start producing quite a bit more energy. So it's a very dynamic situation. It really depends on your activity, placement on the body, what how you're going to connect to the body, and so forth. I'm not going to talk a lot about piezoelectric and human motion, but you run into a similar, you know, to think through the logic of how you go through that. Basically, you can say you've got small-scale motions that are low frequency, such as breathing, heartbeat, you know, maybe finger tapping or whatever. And then you've got these large-scale motions where you've got heel strides, arm, leg motions, elbows, knees, and that type of thing. If you have a piezoelectric scavenger on a machine that's running at, you know, several hundred or several thousand RPM, you get lots of advantages. Basically, every time you're squeezing that, you know, power is basically going to be proportional to the number of excitations. And so for, you know, piezoelectrics on machines, the high frequency really helps you out a lot. So on humans, it'll be the same thing, but when you're operating at hertz rates, even if you work really hard and you're running twice as fast, you know, it's, you're not going to be up into the kilohertz. Resonance, okay? If you're on a machine and you've got a high frequency, you can make your cantilevers or your spring mat system to be relatively small, right? Because as you either increase the stiffness or shrink the length of a cantilever or something like that, its resonant frequency goes up. So if you want to exploit resonance, so you can get larger strings when something's bending in resonance, and to get higher piezoelectrics. Again, you know, you have this frequency relationship, which is disadvantageous for humans. And part of the consequence of that is to have something on the human where you're operating at in the hertz type of ranges. If you want to have a resonant type system, you need to have larger objects to be able to get that lower frequency. But there's lots of games that you can play to be able to do this, and so it ends up being a complicated situation. Piezoelectrics, just to remind everybody, basically you have two different types. You have the ceramics, where basically you can take a ceramic at one temperature the atoms are relatively mobile, and then what you do is you basically heat it up under electric field, and you get all the dipoles to align when they freeze, and so then you end up with different dipoles that are plus, minus, and so on. And so you go ahead and, if you look at this, you end up with positive charge up at the top and negative charge at the bottom, and when you're pressing it, you're producing changes in charge and voltage and so on. The same thing happens with certain types of plastics, except here what the chemists have figured out is that you could have the little dipoles be between the fluorine and carbon atoms in the molecules, and so if you're in the right phase, you can go ahead and you can pull the plastic to be able to get your characteristics that you want. So the ceramics typically have much higher coefficients and in a sense can be more efficient, but they have very little ability to have large strengths. The polymers, on the other hand, are nice and bendy and can have large strains, but typically have smaller coefficients. And so you need to think about those types of things when you're designing your piezoelectric harvesting system. You don't have to use piezoelectric harvesting. These hybrid type systems or magnetic systems or maybe an alternative. It's not necessarily going to be suitable for all cases, but one interesting thing is that since Faraday's law scales independently of size, if you start having suitable micromachining techniques, which get complicated when you're dealing with magnetic materials, you can actually get fairly high power densities and pretty low volumes. So here's something that I think was about 28 millimeters by whatever other dimension gives you, a pretty small generator. It had continuous rotary motion. So when your oscillator on your watch was going around and playing up that spring, basically what it did was it kicked one of these types of devices, spun this as fast as possible until friction slowed it down, and the counter EMF slowed it down, and produced energy. You can set up other systems where you've got some type of coils and magnets moving past each other, and you'll get microwatts in kind of hundreds of hertz range. Then you've got these kind of hybrid systems that I mentioned before, which might be attractive for some systems. So again, lots of other forms of energy harvesting, and there's lots of different ways to kind of come up with solutions. One thing that's attracting interest right now is radioactive sources to make batteries where the radioactive source is emitting electrons, and then so you have a transfer of charge and establishing a voltage that way. So you can basically have what are called beta-voltaic batteries. I think there's probably some social considerations as to whether people want to have radioactive sources on wearable systems. But all the stuff that you learn in your fundamental physics and actually in your biology class too, you can try to figure out where different sources of energy. Trees have a difference in potential from their root system up their trunks, and so there's actually some guys who've been able to exploit that type of bioelectricity. Okay. So let me get back to watches. This is what you're seeing on the market kind of today. You've got lots of different choices, and so I thought it'd be interesting to kind of categorize this a little bit. And if you take these different choices that you have, and you find out what the batteries that they have in them, you see there's actually a huge range in terms of 600 milliamp hour battery down to about 120 milliamp hour battery. You see that you have something that does very little, that basically tells you you've got your Facebook or Twitter or that kind of thing, actually lasts about a year and a half. Whereas you look at the iWatch, it lasts 5 hours. Okay, but it does MP3s, it does acceleration, all kinds of things with a big display. As a metric, we could take a look at the number of pixels. So You could choose not to really have a display, like you have icons instead. So there's 5 or 6 icons here on this type of watch. Whereas if you look at one of these others, you've got basically a full-fledged display. And then the processor choice is interesting. And not everybody tells you what the processor choice is. But you go from having something in the gigahertz down to something, very low power type thing. The radio, there's commonality because of compatibility issues. But you do see some interesting choices of near-field communication in addition to Bluetooth, or having Bluetooth and Wi-Fi. And then your choices of your operating system. So, right now it's kind of like the Wild West. There's everything going on and everybody trying everything. So, in this case, big battery, big processor, that seems to make sense. Similarly, very long lifetime, no processor, that seems to make sense. So what you can do is you can say, well, let me plot some of these different parameters and see if I can try to understand what's going on. And if I take a look at the milliamp hours versus time, or log time in seconds, it's actually confounding because your larger batteries are giving you lower operating times, right? So that's probably saying something that you would expect that if you had a bigger battery, you ought to be able to operate longer, right? So it depends on what people are putting in. You see that there's a kind of a correlation between the number of pixels that are being used and the lifetime. So more lifetime, or bigger displays, less lifetime, generally. So that seems to make sense. If you take a look at the processors that are being used, you actually see that there's a kind of a grouping of these low power type processors where people are getting performance on the order of kind of 3 days to a week. But this also is kind of showing you that you have different situations where people are managing their energy very, very differently. So in this case, you've got a huge battery. You don't have that huge of a processor, and you've got a fairly large display, but not an extreme display. But the lifetime is miserable. And so it's not just the hardware that's giving the short lifetime in this type of issue. It's a system design of the software and how you're operating that hardware. And so that's a kind of an important point. If you take a look at this Galaxy watch from Samsung, you can see they have a pretty low battery, but they've got, at least compared to these, but they actually have a big display and quite a bit of capability. So they're probably doing something clever in terms of how they're putting their system together. So when you're putting your systems together using sensors, you want to think about those types of things. I think I've got another few minutes, so I'm going to race through some other things. Accelerometers, microphones, cameras, they're becoming commodities. Power, size, price is all dropping. They're going to be used in more innovative ways. Like, how are people using microphones for health? Since they're becoming a commodity, there's lots of opportunity. Same thing with cameras. There's all types of apps on your cell phone now that you can measure where your camera is being used as a sensor, where the guys who designed the camera as an imaging sensor never imagined. So you can measure your pulse rate and all kinds of neat things. GPS, still power hungry, but it's being supplemented by other information. Where was the person previously? So you don't have to go through the whole acquisition. The amount of energy that's captured from the satellite is actually very, very tiny. But you take about a joule of energy to go from dead stop to having a good fix, which is quite a bit. But if you've only had to gather, microwatts of energy, if you get that information, you send it off into the cloud, and they do some type of computation away from your device, and it tells you the location. Is that good enough? And so Microsoft has been working on some things like that. And then the health sensor issue. So accelerometers on humans. I've got the thing that I'm wearing is one of these misfits. It's kind of a fun thing. You tap on it, and it tells you how far you've gotten. I've got a Fitbit in my pocket. They're all hard form factors. You know, things drive me nuts is things like me leaving them on the counter, or dropping them and rolling underneath the couch and stuff like that. It's not so much the technology, but it's how it gets integrated into how I use it starts to become important. If we start thinking about why we want to do this gets back to what Vina was saying. We want to create kind of a control loop between having sensor modalities, then the biology side and the environmental side, being able to bring these correlations together, get that information to the clinicians, the individuals, and the caregivers, okay, and then have a feedback loop where they can go ahead and change things. So if we start looking at that in a little bit more detail, we see that for the electronic skin interface, we have a big opportunity, and people already explained this in terms of EKGs and ECGs. It's a low-power system. You can get those. You can measure potentials at a relatively low power. If we look at biochemical sensors, you can actually also have a really low-powered system if you can get the fluids and handle the fluids or chemicals to the position where you can measure them. Optical and acoustic, I think people have got to be clever to be able, typically higher power type things. And then the environmental will depend. I mean, some things you get almost for free, like temperature. Almost to get a temperature sensor on a chip is pretty trivial. You've seen this slide, lots of different things. You're starting to see interesting things about how you get sensors attached to the body in terms of these patches and then also these skin tattoos for different things. People ingesting electronics to be able to see how things are happening inside your body. So you swallow a little pill, and that pill gets powered by essentially the corrosion that's occurring as it goes through your digestive system, and that sends information out to to a patch. So as one example, and Vina touched on this, EKG systems. There's several things coming out. They're using tens of milliwatts of power. Ben Calhoun, one of our partners at UVA, was working on this and looking at a system on a chip approach. So this is a chip he fabbed in not a particularly aggressive technology, but a technology that's very good for low-power electronics. It's got a 4-channel analog front end. It's got power management. This is the input for the thermoelectric. So the thermoelectric, it gets energy is there. The system turns on from a wake-up pulse. The boost converter brings that up to the voltage that the rest of the chip can operate on. There's a processor here that takes that analog front end, does some signal processing, and then there's a radio that transmits it out. So you've got a lot of integration. They're doing lots of multiple functions on this chip. So to manage the power variability of power, since you've got that ability to both analyze the signal and to be able to manipulate it, here's a test where they lowered the voltage coming out of the thermoelectric, and then depending on what's happening, the system behaved differently. So initially, it was transmitting all the information. It starts to not have as much energy available. It says, okay, I don't need to transmit as much, but I'm still going to go ahead and acquire my information. You get to some point here, it says, I just don't have enough power to do anything, I'm going to go to sleep. But then the power, it says, oh, well, power's coming back, let me get going again. And then it goes ahead and goes. And so you need to have those types of smarts in a system. And then what information do you need to send out? Well, the doctor doesn't necessarily want to look at a complete EKG signal. Maybe he's more just interested in heart rate variability for some reason. And so maybe you only need to have the intervals between the different heartbeats. So you could do that type of computation on the chip and then only send out the heart rate information rather than having to send out the whole EKG system. So again, there's an energy consideration and an energy balance to be thought of. We're interested in environmental sensing. There's lots of different approaches. This kind of takes the point of view of metal oxides. They're typically heated, so they use lots of power. So we've been trying to figure out different ways to look at different techniques to be able to do very low power sensing. One thing that since we're a nano center and we need to have nano in our applications, we care about nanowires. And so if you look at the temperature rise of a nanowire, it's a kind of hefty current pulse, but for only about 5 microseconds, you're about 10 microwatts, or 10 microjoules for that. That's a low amount of energy. And so if we can pulse these nanowires and measure their properties on a chip, which also means that we might have an array where we could measure different nanowires in response to different gases, or we could have different nanowires that maybe aren't all good or all have the same response, but we have enough of them to get an idea of the statistic, we might have a way of making a sensor. And so we're working on ways of being able to get nanowires basically onto chips in very controlled fashion, and we actually, this is an older slide, but we can do this. We're putting atomic layer coatings on on nanowires and looking how that changed properties, or just making nanowires. Metal oxides, a lot of people are skeptical of their performance for some ENOS type applications and other type applications because of selectivity issues. We can also look at selective polymer coatings. The tuning fork in a wristwatch operates very precise frequency. It's temperature compensated, that type of thing. If we put a little thin wire of this case almost macroscopic wire of polymer, what we can do is we can watch the frequency tune. Or Omer at NC State has also worked on having arrays of transducers that, when they have coatings on them, react in response to gases, and being able to measure gases that way. Okay. Pulse oximetry systems. Again, you can do a survey of the literature, and you can see where your commercial pulse oximetry systems are. This was actually a big press announcement that they could do a less than 47 milliwatt pulse oximeter, but there's a lot of signal processing that's going on by Masio in this type of application. IMEC had a Thermoelectric with a radio and then a pulse oximeter on a finger as a system. They had to duty cycle it to be able to get the power down. But if you look at this diagram here, the analog signal processing is taking quite a bit, and the LEDs are taking quite a bit. So one things that we're looking at is that we've taken gallium nitride, we use that to optically pump another material, so we get 2 wavelengths in one light pulse. So we can eliminate one of the LEDs. It turns out that you can go ahead and you can at least get a pulsatile waveform at both of these different wavelengths doing this. Another approach is if you want to do multispectral wavelength thing, you can do a similar type trick where you can have the higher energetic photons from the one LED pump other materials. And so what we can do here is we can actually switch these different bands of light on and off from the near infrared to the through the visible. And so we're trying to explore whether or not we can do pulse oximetry that way. So this is a device that we made at NC State. This is a company valence cell that has been putting other devices and then tested our device by putting it into an earbud. So when you go jogging, you're measuring the pulse oximetry in the ear. So it's a nice form factor. The skin interface, as Vina mentioned, is extremely important in terms of how you try to do different things. And so we're spending a lot of effort trying to understand how to capture sweat, how to move sweat, how to be able to understand the hydration of the skin and the body and things like that. And then we're very fortunate at NC State that we have a textile school. And so my colleague Jesse Jur has been making textile type patches in a modular form factor. Or this was actually an undergraduate project where we 3D printed wristbands and put thermoelectrics in them. But when we think about, the picture I showed you of all the accelerometers, all in a hard shell case, maybe it doesn't have to be that way. So you could have different textiles where you have screen printing or embroidery that's giving you different functionality of these different types of materials. And if you go ahead and think about where textiles electronics is, you'd say, well, you know, that's not kind of what I want to have next to my body, right? But you know, if you think about where transistors were, you wouldn't want to have that sitting on your desk either, right? And so there's a progression that we think we're at the beginning at. And industry also thinks that. So this is a commercial wearable textile example where these are electrodes that they've gotten integrated into this, and so you have a heart monitor, and then you know, it's a system, a wearable system that you can go ahead and use. And so we're interested in these types of things. The quality of information that we get, just the EKG is an example. We could really push to have a very high quality signal, or if we have fewer sensors, maybe fewer leads, maybe not as good you know, maybe motion artifacts and other things, maybe we don't have as good a quality of information. So there's a continuum here that we're trying to understand. You know, where do we want to understand the information in our system? How is that going to work? As part of that, for example, you can go from having commercial electrodes to screen printing electrodes to having silver-coated yarn type electrodes, and then see how the different signals behave. And so we're trying to partner with people who have lots of experience in these areas. Adhesive Research makes a lot of hydrogel electrodes and hydrogel type materials for lots of different applications, and so we've been interested in talking to them. You know, how are these things going to, you know, look like? What's the progression of these things? So here's a patch. You know, today we have a rigid circuit board with a lithium polymer battery, but at least it's starting to look like a wearable system. You know, so we're having conversations with some of other partners. How do we make this flexible circuit board, that type of thing? And energy harvesting. And this was just a fun thing we did over the summer. But you know, when you think about what you're wearing on your body, you know, different ways that you can do it. Here you can see from the thermal image, you can see how much heat is coming out of this artery. And this is kind of just a fun demo. And again, this was done with undergraduate students where we have 3D printing. We go ahead, they printed out, they designed it, we put the thermoelectrics in, and then we put a little data logger on it, and they could walk around and they could go ahead and see you know, how much it was producing. So there wasn't a lot of thermal engineering in that, but it was a good conceptual exercise to understand some of the issues about how you get something to be wearable and how to use it. And then finally, you know, for the students in the audience, I think we have about 25 or so. You know, simplicity is sometimes a winning strategy. This is a team of students that were taking a product innovation class, and I said, well, why don't we try to make a peak flow meter a little bit smarter? And over the course of the semester, they said, well, you know, you blow into something, you can get a little fan to turn, and so they connected that to a little cell phone motor and a little microprocessor, and then they went through another generation and they thought we had a design student who thought out the case and how all this would work, and so now what they have is they have a little system that they can blow into. They'd like for it to be self-powered. You get enough current for a short duration of time when you blow into that little fan, because they're using a low-power processor. And they actually have an accelerometer on here too, so they can see what the angle is. That they can get that, they ought to be able to get rid of this battery, and so they potentially can end up with a little system that about the size of a cell phone that's not going to embarrass hopefully, you know, someone to be able to pull it out and use it, so it'll be comfortable and useful for the consumer. And so they entered some contests, and I was very excited to hear that they actually just won the NASA Tech Briefs Metal Provides category for Create the Future contest. And so I think this is a very hot and interesting area, and there's lots of opportunity from, you know, professors like myself all the way down to middle school students to understand how technology affects, and as a grad student especially, this is a very exciting time to be involved in these types of things. So I'll take any questions.
So one of the things you mentioned is potentially harvesting blood glucose, and then obviously we talked a lot about thermal. Can you comment on the safety aspects of that, especially in terms of anything you're taking from the body And if you're also measuring the pulse ox and you're taking heat from that region, then that's also potentially confounding the reading you're getting there.
Yeah, so the question is, you know, can your drawing energy from the body confound your other measurements? And then another part of the question is, what was the first part?
Just kind of the safety aspect.
Oh, the safety aspect. Yeah, well, okay, so the safety aspects is very interesting. When we formed the center, we made a strategic decision that we wanted to be minimally invasive. And a large part of that was not because we were afraid of doing invasive type things, but in terms of the regulatory requirements and being able to go through that, we thought we could learn a lot by doing minimally invasive stuff first and then go forward from that. The FDA recently has done some changes in terms of what medical devices and how they're classified. And so, for example, cell phone apps, if they're now doing medical things, have more oversight than they did, say, a year ago. So it's a very dynamic, changing area. The other piece of that question that's hard to answer is the privacy concerns. So you know, what happens with all this data? How do you keep it private? You know, what happens to your power budget when you start encrypting signals? I mean, if you're severely constrained, you might not want to have that overhead. For the confounding measurement part of the question is for some of the things that we don't know yet, and so we'll figure that out as we go along. But the simple answer is we'd probably try to have the sensor slightly removed from where we're extracting the heat.
You mentioned at the beginning, and there's lots of radios in the room. Is there an opportunity to scavenge those signals or harvest power just from the wireless signals that are being sent?
There are certainly people who are interested in that and doing that. And it really depends where you are in proximity to the transmitter and the frequencies at which you're trying to do it. If you had systems that could work at sub 10 microwatts, then that ambient kind of energy scavenging might start to become attractive. I think that a lot of things that we're looking at are at least up in the 100 microwatt kind of thing. That's different than if I have like a cell phone that's very close to the thing and I'm beaming out maybe almost 5 watts of power from the cell phone and I'm in close proximity. And so it really becomes, if you can put yourself in a situation where you can have kind of a directed RF energy scavenging, I think you have opportunities. Where if it's generic ambient, it really depends on the complexity of the local RF environment. So it's not a very good answer there.
In the very presentation, you compared basically different modalities that you can scavenge energy from human body. My question is, with your current experience, regardless of what was in the proposal initially, because now you have done the research, you have looked at the literature, compared it, which modality would be the winner, you think? Your opinion 2 years into this type of research, if somebody wants to invest time and money, which one would be worth looking into more?
It really depends on the system. So it becomes an application driven question.
It's scavenging from the body. That's the
right. Yeah, but even there, it becomes complex. So, for example, the thermal from the wrist, I think, is feasible, and I think you'll actually see some people doing some interesting things with that in the very near future. That I'll say is probably going to be maybe first in terms of doing something. But there's enough stuff actually in the implantable side where you'll also probably see things where piezoelectrics and different form factors are going to be, in particular, there's a lot of interest in the heart, that may become practical. But to go through the regulatory process to be able to get something like that done that's probably, that will delay that being seen.
But then you started your presentation with wristwatches and what you guys have been doing for 2 decades. What about those?
Well, I think you'll see some thermally powered wristwatches probably relatively soon. But those products failed, and for some good reasons. The Seco product was in Asia, and a lot of Asia can be very warm, and so there wasn't a lot of temperature difference, and it was also very expensive. I mean, I forget what the number is, but it wasn't a $100 watch. It was a couple of $1,000 watch, right? And so if it's a status symbol, so the wristwatch thing, it becomes a status symbol question as well. So I'm not trying to dodge your question. I think batteries are so good that for a lot of things you'll see batteries first and remain first, but you'll see some batteries being supplemented or reduced in size to a much smaller size, but maybe having a supercapacitor or something, or having some other mode of capacity in the system, assuming that the footprints don't get too big. So it's maybe too complex for a short answer.
Considering whether the power system should be updated,
Yeah. So if I'm sitting still in my office and it's reasonable temperature difference because I have the air conditioning going, I'll still produce a lot less energy than if I was walking for the same temperature difference. So it's not just temperature difference, but it's the activity and the temperature difference, largely because of the way you get energy to the cold sink, that thermal resistance of that. And from a system level, you are probably going to want to monitor what the temperature differences are as part of your system design. And so you can get that from both the power of the Thermoelectric, but also from having external temperature sensors, right? And then I think the other piece of that, you get into the contextual awareness of how the sensor is being used. And so if you've got a very predictable type of pattern or cycle, and your electronics are smart enough to kind of recognize that, maybe become smarter about how it stores power for certain situations, and it may use that temperature information as part of how it reaches those types of decisions.
Think about using information of the body as an energy source, includes like thermal energy, whether
Well, the generators are actually really pretty neat devices if you think about it. And so there's been a variety of people who put different types of generators into heel strike devices. And so if you can compress, have some compression, some distance, and some type of ratchet that then spins something up to a high speed, you can generate a fair amount of energy, very similar to like a hand cranked radio. Right? For piezoelectrics, it's more complicated. You have both these small motions and these large motions. So if you have something like in the straps of a backpack and you're walking along kind of like this, and your backpack is going like this, and you've got piezoelectrics within the straps of your backpack, you actually have a large load mass, and then you've got a fair amount of stretch. And so that's a case where you kind of augmented the body by having something that you're wearing that is able to mechanically couple that energy of your motion into something where it could exploit the piezoelectric better. Small. I think I'm getting some signs that I'm running out of time. But, any other questions?
So what's your position about the digital light?
I'm very interested in it. we in the center, we didn't choose that as a research thrust because there's so much research investment in solar. But I think that using solar makes a lot of sense for a lot of applications, and especially since people don't spend all their time. If it's people, they aren't spending all their time inside. So if you've got a desk lamp, or if you've got some type of smart lighting system that's illuminating areas that's smart enough to understand where something can be illuminated, it's probably a nice way to capture energy. Okay, 10:22. So it's the
Break.
Okay. So I think we're in the break. I'll be happy to answer any questions during break.